So last time, remember, we were looking at coastal areas with depositional features. These were places undergoing net sedimentation and included spits and baymouth bars, barrier islands, and things like that. There are other coastlines, however, that are undergoing extensive erosion. And those erosional features are things like wave-cut cliffs, marine terraces, wave-cut platforms, sea caves, sea arches, and sea stacks. Now here, for an example, is a wave-cut cliff which forms when the surf erodes directly into the cliffs. And over time, the overhanging rocks will eventually collapse into the sea, and the entire coastline will simply migrate landward as a result. Notice in this particular figure that there's no beach whatsoever. Any sediment that is deposited is quickly removed by the strong wave action that's occurring within this particular location. Now, erosion by waves can also plane the rocky surface directly beneath the surf zone, creating what's called a wave-cut platform. And in this figure, notice that the wave-cut platform is being extensively eroded by the strong surf within this area. But then subsequent uplift of the wave-cut platform will then form a marine terrace, as shown to the right. Here's some other erosional features, which include sea stacks and sea arches. A sea arch both features are simply due to erosion of the bedrock along the coastal area by strong waves and currents. And so the sea stack is essentially just a piece of the mainland that's been left behind by the encroaching sea. And again, if you look closely, well, we do not find any beach whatsoever because, again, any sediment that's produced is quickly carried away by the strong waves. Here again, we see a series of sea stacks, which are basically remnants of a shore erosion. The lithology, the rocks comprising the sea stacks, are the same as those occurring on the mainland along the, as exposed along the sea cliffs. And again, virtually no beach whatsoever. Now let's look at a couple of different examples of actual coastlines, beginning with the Atlantic and Gulf coasts. Now the characteristics of these particular coastal areas include such things as, one thing, they're tectonically stable. These coastal areas do not contain plate boundaries. Instead, they're basically passive continental margins. And as a result, they're characterized by having very broad, gently sloping coastal plains, in addition to depositional features like barrier islands. And some may even have what are called estuaries, which are basically drowned river valleys along those portions undergoing submergence. Problems along these particular coastal areas include overall coastal submergence, erosion, and also urbanization of barrier islands, which would then require the construction of artificial barriers to keep the barrier islands themselves from gradually eroding away. And we'll take a look at how at some of the attempts to try to alleviate coastal erosion a little bit further on. But first of all, let's look in more detail at what are called submergent coastlines. A submergent coastline results from overall coastal subsidence or global rise in sea level, and are typically characterized by irregular shorelines and drowned river mouths that are referred to as estuaries. Here, for an example, are several estuaries located along the Atlantic coast, such as Delaware Bay and Chesapeake Bay. And estuaries basically constitute drowned river valleys that are characteristic of coastlines that are gradually sinking or being overtaken by, or gradually being overtaken by the ocean. The Atlantic coast, for the most part, is characterized as relatively stable with flat beaches and barrier islands. But again, as sea level rises or the land subsides, the invading waters can then flood river valleys, in which case we get estuaries. Now, estuaries are actually quite complex ecological systems because they're kind of a mixing zone between fresh water from the continent and salt water coming in from the sea. And as a result, the ecosystems tend to oftentimes be quite fragile for the most part. Other coastal areas are undergoing emergence. An emergent coastline results from uplift or overall drop in global sea level, and are characterized by exposed wave-cut cliffs and wave-cut platforms, as shown in this particular photograph. The Pacific coast, parts of the Pacific coast are emergent. For example, and those sections are characterized by narrow beaches, steep bedrock cliffs, wave-cut platforms, and also elevated marine terraces. The problems include the narrowing of the beaches, oftentimes due to the loss of sediment as a result of damming of rivers upstream of the coastline. And the construction of dams upstream basically will trap sediment, and the sediment will accumulate behind the dams and never reach the coastal areas where replenishment or renourishment would typically occur. And once the beaches disappear, the cliffs behind the beaches will erode even faster, because then the waves are hitting directly against the cliffs, accelerating the rate of erosion at that particular point. Here, for an example, we see elevated terraces along the coast of California, again caused by coastal emergence. At one time, these terraces were lowered within the surf zone where these terraces were planed by the surf, but then afterwards uplifted, as shown in this particular photograph. Again, notice that there's no beaches or very little beach at these particular locations. Now, coastlines can gradually evolve over time. For example, here we're starting out with a evolving coast that's initially irregular with erosional features. And again, those erosional features include sea arches, sea stacks, wave-cut cliffs, and things of that nature. There's virtually no beach at this point because any sediment, again, that's produced is just carried away by the waves and the currents. But then, over time, if the coastal area is stable, the coast will gradually become straighter and flatter over time as depositional features begin to form. And here, for an example, we see the formation of a spit and a tombolo and the beginnings of a beach ahead of the wave-cut cliff. So deposition, sedimentation is beginning to take place along this particular coastal area. And eventually, a straight coastline with depositional features will emerge. Notice now that the original spit in the previous diagram has now extended all the way across the cove to form a baymouth bar. The former wave-cut cliff now has a nice beach in front. And we also have a spit extending offshore further towards the right. Notice again the direction of the longshore current. And as a result, the spit will extend offshore in the same direction as the beach drift and longshore drift is carrying all the sediment down in the down coast direction. Now, coastal areas that are undergoing erosion have serious problems, as shown in the photograph. And so it's important to try to stabilize the shore any way we can. Factors that affect erosion, shore erosion, include such things as proximity to sediment-laden rivers. If the coastal area is close to a mouth of a river that's bringing in lots of sediment from the mainland, then any sediment that's removed from the beach is quickly replenished by more sediment. On the other hand, coastal areas that are far removed from sediment-laden rivers will not be receiving any sediment or very little sediment to replenish any that was lost by erosion. Also, degree of tectonic activity, whether the coastline is undergoing uplift or subsidence, those will certainly have effect on the rate of erosion, as will the overall topography and composition of the land. Wind and weather patterns are also important factors. Coastal areas that are dominated by strong offshore winds blowing landward will typically have lots of wave action causing extensive coastal erosion. Weather patterns, particularly tropical storms and hurricanes, are very detrimental to coastal areas. Also, the configuration of a coastline and nearshore areas. Remember that headlands, those coastal areas that extend offshore, are typically subjected to convergence in terms of wave refraction, so that wave energy is maximized along these headlands. And as a result, headlands tend to erode quite quickly, whereas coves or other types of recesses within the coastline are places where wave refraction tends to spread out. And as a result, these are places that are receiving minimal impact by incoming waves and are likely or most likely to have beaches developing within those coves. Now, there are different ways of dealing with shore erosion. One way is to the construction of various structures and barriers that include jetties, groins, breakwaters, seawalls, geotubes. I'll show you some pictures or some examples of these different structures. Another thing we can do is beach nourishment. Simply truck in and add more sand to beaches that are eroding away. And of course, if all else fails, simply pick up and relocate the buildings. Now, jetties are structures that are constructed at entrances to rivers and harbors. And jetties interrupt the movement of sand, particularly sand being transported by beach drift and longshore currents. The net result is sand is deposited on the upcurrent side of the jetties. On the other hand, on the downcurrent side, those beaches are primarily undergoing erosion. Again, if you look at the direction of the longshore current in this figure, we see that the net deposition is occurring on the jetty facing the upcurrent side of the coastline. Now, a good example of a pair of jetties are the ones constructed at the entrance to the boulevard roads off the east end of Galveston Island. And in this particular photograph, you can see the jetties extending offshore. If you're going on the Galveston field trip, our first stop is going to be right here at the end of this of Seawall Boulevard. And we're going to take a look at these jetties and discuss the various features of these structures in a little bit more detail. But if you look closely, you can see that the ships are entering and leaving the harbor between these pairs of jetties. Now, the purpose of jetties are, one purpose of the jetties is simply to help to keep sediment from accumulating within the harbor. When sediment accumulates within harbors, this requires expensive dredging to deepen the harbor in order to allow large ships to enter and leave. Another purpose of jetties is to keep waves out of the harbor channel, allowing for safer navigation. Here, for an example, we see a couple of pairs of photographs of the North Boulevard jetty on the northern side of Boulevard Roads. This particular jetty extends 5 miles out into the Gulf. It's a very huge, very long structure. Now, here in this figure, Galveston Island is to the left, and the Boulevard Peninsula is to the right. And in between is the entrance to Galveston Bay. And here I put in the jetties as a couple of or a couple of red lines. Now, in this particular location, water enters the bay between the jetties, depositing a flood tidal delta in the process. The waters can enter the bay, for example, during high tide, but more likely at this particular location, wind patterns, particularly strong winds blowing inland from the Gulf, are probably more influential in pushing water into the bay area itself. There are other times when the water exits the bay, carrying sediment Gulfward. This could occur, for example, during low tide, or more likely when we have strong winds blowing down from the north, pushing water out from the bay into the Gulf. But oftentimes, longshore currents will parallel the coast and be moving from east to west. And where longshore currents encounter the jetties, notice that the currents are deflected around the jetties and pick up sediment leaving the harbor in the process. On the other side, off the south jetty, currents will reverse direction behind the south jetty and actually deposit sediment against the jetty. Some of this sediment can even spill out into the harbor. Depending on the wind patterns, the currents can also reverse direction, and at times longshore currents can flow eastward, and this has the effect of piling up additional sediments against the south jetty. So the net result is that the south jetty, indicated or traced by this red line, shows a lot of sediment buildup along both sides. A lot of that sediment has actually spilled over into the harbor, creating that landform, which is shown in this particular photograph. If you're going on the Galveston field trip, our second stop will be Apfel Park, and we're going to look at this huge buildup of sediment right against that south jetty. This is one of the few stretches of beach along Galveston that's actually growing at a rate of several feet per year because of these processes. Basically what's happening is that the jetty is just causing all the sediment to pile up around it. And as a result, this is one of the few constructional beaches that are found along Galveston. Now, groins are structures constructed at right angles to the beach. And the groins, for the most part, deposit sediment on the upcurrent side, whereas on the downcurrent side, there's extensive erosion because of the sediment pore nature on the other side of the groin. Typically, groins are constructed in series at right angles to the beach. For example, if you look at this particular photograph, notice that the sediment is building up on one side of the groins, whereas on the opposite side there's net erosion. In this photograph, what's the overall direction of the beach drift and longshore current? Is it towards the upper left-hand corner or towards the lower right-hand corner? Just looking at the photograph. You mean the direction of the longshore current? Yeah, look at the side of sediment accumulation along the groins. This gives you an idea of the direction of the longshore current and beach drift. So in other words, here in this inset, the longshore current is going from left to right. And notice that the sediment is piling up on the upcurrent side of the groin. So in this photograph to the right, we see that the sediment depositional pattern indicates that the longshore current is moving towards the upper left-hand corner of this photograph. Do you see this? Yeah, they were looking at, in other words, the longshore current is flowing towards the upper left-hand corner of this photograph, judging from the depositional patterns along the series of groins. Now here's a few photographs of the groins in Galveston. Again, notice that they're constructed in series perpendicular to the beach. And the purpose of the groins, they're trying to keep the sand and the beach in place, but unfortunately these groins are not very effective because notice that the waves are simply eroding away the beaches between the groins. So although we have sediment buildup adjacent to the groins, in between the groins we're losing beach, as shown by those white arrows in the lower right-hand corner. And we're going to take a look at this in more detail on the field trip. Seawalls, on the other hand, are constructed behind the beach. The main purpose of seawalls are simply to protect the structures behind it in the event of tropical storms and hurricanes. Unfortunately, in the case of most seawalls, the sand becomes blocked behind the seawall and is unable to replenish the sand that's lost on the beach itself. So that over time, unless the beach is renourished, the beach will eventually disappear, as shown in this particular photograph. This is a section of the Galveston seawall towards the west. So here again, we're looking at the aerial views of the Galveston seawall. And again, notice that there's no sand on the beach ahead of the seawall. It's all been eroded away. And over here we see where the seawall ends. And if we go beyond the seawall towards the west, notice that the beach is being eroded landward. So the seawall is doing its job in protecting the structures behind it, but unfortunately, because the seawall is also blocking sediment behind it from nourishing the beach, over time the beach disappears unless. Now, breakwaters are structures that are constructed offshore and parallel to the coast. So in this photograph, notice that where the breakwater is identified. The purpose of breakwaters are mainly to protect boats from the force of large incoming breaking waves. So it's not surprising that yacht clubs tend to be located directly behind the breakwater. Also notice that if you look at the beach tends to become wider behind the breakwater. And this is because of the disruption of the longshore transport that causes the seaward growth of the beach directly behind the structure. Another reason why the beach is wider is because the breakwater, as the name implies, reduces the impact, the force of the incoming waves, so that the beaches behind the breakwater are not as extensively eroded as the beaches on either side. Here we see some critical erosion rates in feet per year along Galveston beaches. Over here at the entrance to both roads, the entrance, as we saw before, between those pair of jetties into Galveston Bay, the greens indicate net deposition. And again, I showed you this photograph several slides back of Apfel Park, directly behind the south beach, the south jetty. That beach is growing by about 8.9 feet per year. And just behind the north jetty, that beach is growing about 11.9 feet per year. And those are indicated by these green segments. However, as we move further towards the west, the red and the orange segments are stretches of beach that are undergoing net erosion. In other words, the beaches along those particular sections are disappearing at a rate of several feet per year, and that's really where the problem is along this particular section of the Gulf Coast. Some parts of the Gulf Coast, particularly far to the south here, are losing beach by as much as 10 feet per year of beach erosion. So we're going to, tomorrow, or during the Galveston field trip, we're going to look at these eroding beaches in more detail also. It's not surprising that the areas that are undergoing, the beaches that are undergoing net deposition and growth are those stretches that occur adjacent to the jetties, where those structures act to kind of trap sediment and keep it in place. Here's some examples of erosion of Galveston beaches. In the upper photograph, notice that retreat of the shoreline has brought some of these structures precariously close to collapsing. Along some parts of the Galveston coastline, geotubes have been buried, the purpose of which is to keep the vegetation line from eroding any further back. And we see in these figures, these series of figures of geotubes. A geotube is largely a large latex tube that's filled with sand. And what they do is they bury these geotubes right along the vegetation line to keep the vegetation line from eroding any further back, any further. And the reason for that is because of the Texas Open Beaches Act, which states that any beach seaward of the vegetation line is public. And as a result, you cannot build private structures on the beach ahead of the vegetation line. If a private structure is constructed behind the vegetation line, but then erosion moves the vegetation line behind the structure, that structure ends up sitting on the public beach, and at that point has to be torn down or moved. And that's why they bury these geotubes, to keep that vegetation line in place along the erosional parts of the coastline. Unfortunately, strong wave action has exposed these tubes, as shown in these particular photographs. It's not only the Gulf side, but also the lagoon side of Galveston Island that's undergoing extensive erosion. And here in this figure, we see some of the erosional rates in feet per year on the lagoon side. And we can see erosional rates of anywhere from 4 to 5, even as high as 6 to 7 feet per year occurring along the lagoon side. Now, Galveston Island State Park has made several attempts to keep the lagoon side from eroding, and have actually tried to reclaim some of the land that's been lost. One particular attempt was to construct these terraces, basically a grid work, the purpose of which is to trap sediment. And the idea is that if enough sediment accumulated within these terraces, eventually a saltgrass could take root and reclaim that part of the lagoon that has been lost as a result of erosion. Other attempts have been the construction of geotextile tubes a little bit offshore to serve kind of like breakwaters and minimize the impact of waves and currents along the coastline. We're going to stop and take a look at these structures on the field trip and see whether or not they're actually very effective. If all else fails, beach nourishment is the way to go. Here we have, if you look in the offshore, there's a ship that's dredging sediment, and from there the offshore sand is being brought onto the beach and spread about to renourish the beach, basically. We try to reclaim some of the sediment that's been lost by way of erosion. The problem with this approach is that it's very expensive, and when the beach is renourished, it just simply erodes away again over a time periods of months to years, and so you have to constantly go in and renourish the beach, and it costs millions and millions of dollars per mile in order to do this. And of course, along Galveston, they do this quite a bit, and it's the taxpayers that mainly fund this particular approach. Here is the before and after pictures of beach nourishment in Miami Beach. Notice in the before picture, there's a series of groins that have been constructed perpendicular to the beach, but those groins have not been very effective for the most part, so they simply bring in and add new sand. Unfortunately, over time, that sand is going to disappear, and so they're going to have to keep renourishing that beach over and over and over again in order to keep the tourists coming and to spend money and, keep the economy going. Now, further towards the west, along at Surfside. Surfside Beach is undergoing serious erosion. And the main reason for that is that the Brazos River was rerouted back in the late 1920s. Notice in this photograph the path of the old Brazos River prior to 1920, which emerged at Surfside. But then in the 1920s, the Army Corps of Engineers rerouted the Brazos to its new route further towards the west. And the reason they did this is because the old Brazos River was constantly being filled with sediment brought down from the interior of the continent by the Brazos River. And as a result, they had to go in and periodically dredge the old Brazos to keep it deep enough for ships to enter and leave the harbor and service those industries. But rather than undergoing repeated expensive dredging, they thought that simply by rerouting the river along its new path, sediment wouldn't be brought in along the old Brazos anymore, and this would significantly reduce these dredging, the expensive dredging. Unfortunately, by rerouting the Brazos River, the major source of sediment was cut off at Surfside, and as a result, over time, any beaches that were eroded were not being replenished by new sediment because no new sediment was coming in anymore. And as a result, over the last few decades, Surfside Beach has been gradually disappearing. Notice that in the upper photograph, this is back in 1935, showing the old abandoned delta right after the Brazos River was rerouted. And it's only in the course of a couple of decades that most of it was eroded away by 1954, if you compare those before and after pictures. Notice the pair of jetties, which certainly accelerated the beach erosion in this area. On the other hand, the new Brazos River Delta grew quite a bit over that same period. There was significant growth in only 19 years. Here's some examples of erosion of Surfside. These structures that are sitting on the beach were at one time behind the vegetation line, but have since had to be torn down because they ended up on public beach. And even so, as the vegetation line continues to move inland, those structures behind it are going to eventually be affected in the same way. If you look at the photograph to the left, between the pair of jetties, notice that fine sediment continues to flow out of the harbor at Surfside Beach, but that sediment is being carried far offshore and is not making its way back to the coastline. And as a result, even though sediment is exiting the harbor, it's exiting far from the shore, and as a result does not replenish the beach. Any questions? This sediment, for the most part, is very fine silts and clays. It's not really sand anymore. The sand is being dumped further towards the west along the new Brazos River Delta. Now, hurricanes are the ultimate coastal hazard. Several things are required in order for a hurricane to form. First of all, warm ocean water in excess of 80 degrees Fahrenheit. We need the convergence of low-level winds, typically associated with low-pressure areas. Ascending humid air that occurs within the ascending air within low-pressure cells. What's more, you need calm winds aloft, and finally trade winds to steer the hurricanes. This is particularly true of Atlantic hurricanes that originate off the coast of Africa. But we see that in the bottom photograph, the belt of tropical storms and hurricanes mainly occur between 30 degrees north and 30 degrees south latitude. However, there's a gap right along the equator. Why do you think we do not get what's the way to put this? Why are tropical storms and hurricanes lacking right along the equator? It's the result of the Coriolis force. As the Earth rotates around its axis, it puts a spin to the trade winds, causes the trade winds to kind of circulate. And the equator does not experience that Coriolis force. And as a result, tropical storms do not tend to form right along the equator. The upper right-hand figure shows the area of warm surface waters. These are the conditions that are most favorable to the formation of tropical storms and hurricanes. Now here's a cutaway view of a typical hurricane. Notice that in the lower part, the overall hurricane is a strong low pressure area that circulates in the counterclockwise direction. And the eye wall is where the winds spiral up towards higher altitudes and then diverge at high altitudes. We would expect the right along the eye wall to be the zone where winds and rain tends to be most intense. On the other hand, look within the eye of the hurricane itself. Winds are actually descending from higher altitudes towards the surface. And when you get descending air masses, typically those areas are calm. And as a result, the eye itself tends to be a very calm part of the overall storm system. The lower clouds form the rain bands that tend to spiral inward around the storm center in the counterclockwise direction. Storm surges are associated with incoming hurricanes. There are two reasons for the formation of a storm surge. Out at sea, strong winds pile up a wall of water near the hurricane center, basically the eye. In addition, the eye is a center of intense low pressure, and this has the effect of lifting a dome of water within the eye. So you have both a pressure surge and a wind-driven surge combined that forms the overall storm surge out at sea. Now, as the storm surge approaches the coast, the shallowing of the seafloor aids in piling up the wind-driven ocean to the point that when these surges finally hit land, they're huge and can do extensive damage as a result. Here's an overall profile of a hurricane approaching the east coast of North America near South Carolina. Here we can easily see the eye of the hurricane and the overall counterclockwise circulation. The dirty side, or the most intense side of the hurricane, is the side that's approaching the land. Here, the incoming winds tend to be of highest intensity, and also the rain tends to be the most intense on the storm surge side. On the other side of the hurricane, notice, however, that the winds are blowing seaward, and this creates an ebb surge. So if you're going to get caught in a hurricane, it's better to be caught on the ebb side rather than on the storm surge side. One of the most devastating hurricanes that occurred in the United States was the Great Galveston Hurricane of 1900, which was a Category 4 hurricane when it struck the island back in September 8th of 1900, reaching wind speeds of over 120 miles per hour. The result was that the city was devastated, and an estimated 6,000 to 12,000 people were killed. And because initially they tried to get rid of all the bodies by piling them up on barges and taking them offshore and dumping the bodies, but what they found was that several days later the bodies just washed up again on the beach. So what they finally had to do was just simply pile up and burn the bodies on the island. Here's some photographs of the Galveston Island hurricane. These were mainly taken along Seawall Boulevard, showing the extensive destruction. The hurricane-force winds and storm surge pushed a wall of debris reaching 15 feet in height inland over several blocks. And if you look at the lower right-hand figure, notice that Galveston was hit on all sides by the storm surge. On the Gulf side, that storm surge reached as high as 15.7 feet. On the Galveston Bay side, it reached as high as 10 feet. And the net result is that the piling up of all that debris created this large wall of debris that surrounded the interior of the city and largely protected it from the strong storm surge indicated in this figure. Now, after the hurricane, beginning in about 1905, a seawall 7 miles long and 17 miles high was constructed. Structures were also jacked up during grade raising, and dredges poured anywhere from 4 to 6 feet of sand beneath the jacked up structures, literally raising the island in the process. You can see the before and after pictures in that lower left-hand photograph. Then there was Hurricane Katrina back in 2005, which reached a Category 5 status in the Gulf of Mexico and made landfall in Louisiana as a Category 3 hurricane. Hurricane Katrina is thought to have been the most destructive storm in terms of economic loss, estimated to be up to about $125 billion. And if you all remember, New Orleans was flooded as a result of a breach in the artificial levees. And once the water flooded New Orleans, it just kind of sat there because the pumps weren't working. And because the electricity was out, the pumps couldn't pump the water out of the city. The problem with New Orleans is that much of the city sits within a bowl, even below sea level. So once it's filled with water, the water has no place to go. It kind of just sits there. And so it wasn't until after the pumps were activated again that the water was finally they were able to finally pump the water out. And anyway, that's the story. And then there was Hurricane Ike, which struck our part of the Gulf Coast as a Category 2 storm. Ike was particularly devastating in that it had a unusually large eye, even though it was only a Category 2 storm. And as a result, the storm surge was close to a Category 4 storm surge. And of course, here we have the debris on the Galveston seawall after Ike. If you look at it, if you look ahead of the seawall, Gulfward of the seawall, all of the beach disappeared. And what's more, all that debris on the Seawall Boulevard were the piers and the offshore structures that were completely destroyed, as for example Murdoch's gift shop right after Ike. Here we see the before and after pictures of Ike along each beach. If you look at the yellow arrow, you see just how much of the beach was devastated. And here we see before and after pictures of Ike. This is the south end of Pirates Beach. If you look at the bottom photograph, there are some exposed geotubes that were initially buried, but have since, all that sand has been removed. And here is the north end of Pirates Beach before and after. Again, in the bottom photograph, we see again exposed geotubes. This is the south end of Galveston seawall. This is where the seawall ends. We looked at this before. And we see it right ahead of the seawall. That part of Galveston was particularly devastated. And these are the famous photographs, before and after pictures of Crystal Beach. So anyway, obviously hurricanes are very destructive to coastal areas. Any questions? Our favorite slide.